It turns out that the partial differential equation for this model can be explicitly solved, and this is true for many of the short rate models that have been introduced in the literature. And it's important to note that, as with any research effort, the models that are introduced are partially defined in terms of their the usefulness of their features and the desirability of their properties, and also partially designed to be models for which one can obtain explicit solutions of the problem at hand. So in particular, this model is a model for which the partial differential equation is explicitly solvable, and it turns out that the price of a zero coupon bond has a form which appears one can determine the general process for R which allows this form, but it basically says that the price of any zero coupon bond is a function of a coefficient function of little t and capital T, an exponent function of little t and capital T, and R, the interest rate, the short-term interest rate at time little t. In other words, with this model for interest rates, you can price zero coupon bonds today knowing only today's overnight rate, that's R of t, and then use these functions A and B, which are fixed, and these functions are independent of interest rates, and so they only change with time. And the explicit formulas for A and B are seen here. Notice that the formula for B reflects the parameter A, which we see in the differential in the stochastic process for R. You'll note that the formula for A includes the B term. It also includes A and sigma, which come from the definition of the stochastic process. And it involves this term R bar. And R bar is the formula here, is the rate on an infinitely long bond. In other words, at time t, if we imagined what would be the rate at time t for a very long zero coupon bond, that's what R bar is. And you can see it's in R bar that the Sharpe ratio appears. The Sharpe ratio only appears, it doesn't appear in the B function, but it does appear in the coefficient A function by virtue of this long-term rate R bar, and it appears right here. And this equation was solved assuming that the Sharpe ratio was constant, independent of time, independent of the level of short-term rates. Notice one of the properties of R bar, which is the long rate, is that if you have a sigma is large, as sigma squared gets bigger, the long rate will tend to become negative. So one of the properties we'll see graphically soon is that the Vasicek model, if you have a high volatility model, the longer rates will will drop very quickly. You'll have an inverted yield curve where the short rates will be above the long rates and the long rates will become eventually negative. The Cox-Ingersoll-Ross takes the starting point and the advantage of the Vasicek model in which we have mean reversion, and adds to it an advantage where the volatility term now depends on R, and in particular by way of the square root of R. So unlike the Rendleman-Barter model, where had a geometric Brownian motion form where the volatility coefficient was a sigma R, this is using a square root of R. So this model has the benefit of mean reversion, has the benefit of volatility being related to R. It's also impossible for interest rates to become negative in this model. So it has a lot of the advantages, and this model was quite popular once it was developed after the Vasicek model. This model has been and continues to be a well-regarded and often used model in applications because of these various features, and I'll point out the shortcoming later.